All right, next in this chapter, we're going to jump in and start looking at ions. So first, let's look at the radius of ions. So let's see how, say, forming a cation or an anion is going to change the radius of an atom. Okay, so in order to look at this, we're going to look at effective nuclear charge. So for example, let's compare calcium and calcium 2+. Okay, so we're going to compare those. Okay, so for this, we're going to use just a really rough estimate for calculating the charge. So we're going to use just core electron screening to calculate Z effective. So we're going to calculate Zeph for both of them. Okay, so let's look at the configuration for calcium. So calcium 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. Okay, so that is calcium. So let's then think about what would calcium with a +2 charge be. So +2 means we've lost electrons. So it turns out that the electrons are lost are the highest energy. So it's going to be these two here. So our Ca2+ is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Or again, those ones are the ones that are lost. Okay, so let's calculate effective nuclear charge. So for effective nuclear charge for calcium, we're going to get Z, which is 20, minus S. So S is 6, 7, 8, 9, 10, 16, 17, 18. So as expected, a +2 charge for calcium. Effective nuclear charge for Ca2+. Okay, so still 20. Now this is the outermost shell. Okay, so we have the n equals 4 shell. Now the outermost electron is in the n equals 3 shell. So our core electrons are 6, 7, 8, 9, 10. So 10. All right, so because of that, our effective nuclear charge just went from a +2 to essentially a +10 for calcium 2+. Okay, so let's think about what that would mean for the radius of the atom. So we talked about atomic radii and how essentially what one of the largest effects on the radius is that effective nuclear charge. So a really positive effective nuclear charge is going to draw those electrons in. So what we would expect to see is the radius of calcium 2+ being a lot smaller. Okay, so calcium would be sort of large, and calcium 2+ is going to be a lot smaller. And the reason is that increased effective nuclear charge is able to more strongly attract those electrons and pull them in. So this is true for all cations. So it turns out cations are smaller than their neutral atom. Okay, so cations are all smaller than their neutral atom. And we'll take a look at a figure or diagram of this in just a minute. But before that, let's take a look at anions. Okay, so for the anions, we're going to compare nitrogen and nitride ion. Nitrogen and nitride. For this comparison, we are going to use Slater's rule. So anions, we're adding electrons in, and that's going to be in our same shell. So Slater's rule is going to be better for our comparison here. So nitrogen, 1s2, 2s2, 2p3. Okay, so nitride, N3-. The -3 means that we have added in 3 electrons. So they go into the outermost shell. So we're going to add them right here. So we get 1s2, 2s2, 2p6. Okay, so that is what we have for nitride with those 3 extra electrons. Okay, so we're going to use Slater's rule. Okay, so we'll start with the nitrogen. So we're going to calculate S first. Okay, so our S is, okay, so in the same shell, we have 5 total electrons. Remember, an electron cannot screen itself. So instead of putting a value of 5, we're going to take one away. So that's 4 in the same shell, getting the 0.35. And then we just have what's below it. So we just get the n minus 1, which gets the 0.85. Okay, so our S value here is 3.1. So now for nitride, okay, so now we have 6, 7, 8 in this shell. We have 8 total electrons here. So remember, we can't screen ourselves. We'll take 1 away for 7. And then still the 2 in the n equals 1. So for this one, we get 4.15. So effective nuclear charge for nitrogen is going to be nitrogen's atomic number, which is 7. And we're going to subtract the 3.1 to give us a 0.39 effective nuclear charge for nitrogen. So the effective nuclear charge for nitride with the 3 minus charge, still 7 protons. But now we're going to subtract 4.15, and we're going to get a plus 2.85 for an effective nuclear charge. Okay, so what happened with the anion? When we add electrons in, that gives us more same shell shielding. That's a mouthful. Same shell shielding. So our value here, our 0.35 value went up. Now there's 3 extra electrons contributing to the shielding. Although it's not a huge effect, but it did reduce it down by almost a full value here. Okay, so pretty significant, feeling a plus almost 4 charge as nitrogen and feeling almost a plus 3 charge as nitride, again, due to more electrons being able to shield. Okay, so this is true for all anions. We introduce more same shell shielding. So anions are larger than their neutral atom. Okay, so we get that cations are smaller because we've increased the effective nuclear charge on the valence electrons, and anions are larger because we've decreased the effective nuclear charge on those outermost valence electrons. Okay, so I kind of said that this is true all the time. So let's take a look at the Prezi and the figure in your book. Okay, so we just have a handful of groups 1, 2, 3, 6, and 7, just so we can get some comparisons here. So our neutral atoms, those are in yellow. So lithium, beryllium, boron, oxygen, and fluorine. And we do see as we move this way on the periodic table, they get smaller. And again, that's because effective nuclear charge is increasing. And then as we move down, we see that atoms, the neutral atoms, are getting larger. And again, that's because we're increasing the amount of electron shells we have. So that makes sense that those are getting larger. Okay, so our cations are red. So over here, we form cations in groups 1, 2, and 3. In groups 6 and 7, we form anions. So those are here in blue. Okay, so if we look, lithium cation, quite a bit smaller than the neutral. Beryllium, really smaller, and then boron, like itty bitty tiny in comparison. So kind of look at what that sort of means here. We have a plus 3 charge here, so we're shedding 3 electrons that normally get in the way and shield. So we're really, really increasing the effective nuclear charge for something like this. So you see this whole sort of family, those cations are quite a bit smaller than the rest in the row there. Okay, so again, shedding off a ton of electrons there really, really helps to decrease the size, because again, you're really increasing that effective nuclear charge. And of course, we see the opposite here. So not quite as dramatic as, say, comparing aluminum to sodium, because again, we're introducing electrons into the same shell, and we do know that same shell shielding is a much smaller effect. So the ones where we've added 2 electrons, like in our chalcogen family, are bigger than the ones where we've only added 1, but not as significant as we see here. Because again, it's in the same shell, so they are larger, but not by a whole lot. But they are definitely a lot bigger than the neutral atom. So cations are smaller than their neutral counterpart, and anions are larger, and it all comes back to effective nuclear charge. Less shielding, more shielding, which directly affects the radius of the atom. Okay, so let's get lighting back here. Okay, so we'll come back and look at ions again. Next, we're going to look at what are called isoelectronic atoms. So isoelectronic atoms. Okay, so this is just like a fancy word for same number of electrons or same configuration. So you can build isoelectronic, series for a lot of things, but we're going to see this the most often with everything that has the same number of electrons as a noble gas. So the most sort of common isoelectronic series we're going to see is a noble gas. So for example, let's look at a bunch of atoms that have 18 electrons. So 18 electrons. So if you grab a periodic table, let's see if I have one. A periodic table might be missing, but that corresponds to argon. Okay, so sorry, periodic table. Oh no, here it is. Just kidding. Okay. So we could just grab the neutral atom that corresponds to 18, which is argon. So we can write out the configuration for argon. Okay, so first one, again, the easy one, the neutral atom, argon, 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, argon, easy. Okay, there's a ton of other atoms out there that have the same isoelectronic species, are isoelectronic to argon. If we look on the periodic table, nothing neutral. Argon's the only neutral atom that has 18 electrons, but of course there can be ions. So if we take a look, 18, we had chlorine. For example, chlorine, we know chlorine forms Cl minus. So if you take 17 electrons and you add one more, you get 18. So chloride ion is isoelectronic. Okay, so Cl minus. Okay, so we have 1s2, 2s2, 2p6, 3s2, and regular normal chlorine is 3p5. Okay, so I'm going to kind of put under here. Neutral chlorine has 3p5. Okay, so that means Cl minus, we add another one, is going to be 3p6. Okay, so then we have 3p6. So same electron configuration. Again, neutral has 5. We're forming chloride ion. We're adding one more, and we get 3p6. Okay, so there's some cations also. So let's say we go over here. Calcium does have an ion that's isoelectronic with argon. So calcium has 20, so let's kind of write it out. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So calcium is this. Okay, so this is not isoelectronic. So if we wanted to make this isoelectronic, we would have to get rid of both of those. So if we got rid of those, then the configuration is the same and we have the same number of electrons. So neutral calcium isn't isoelectronic, but calcium 2+ is isoelectronic, where again, we get rid of those two, then we have the same configuration. Okay, so for practice, you could go and look at other species. Sulfide, so S2-, so again, 16. You add 2, you get 18. Phosphide, same thing, adding 1, 2, 3, isoelectronic with argon. And K+ would be isoelectronic. Sc3+ would be, Ti4+ would be, this is probably about the extent of it, V5+ could be. Then once we get past that, not really able to be isoelectronic. That's just removing way too many electrons at that point. Okay, so tons and tons of ions that can be isoelectronic. Again, okay, so again, some that we mentioned. S2-, P3-, K+, for example. Let's see, we have calcium, chlorine. Okay, so we have all those. So if we wanted to kind of look at what we had done in the previous section, let's see if we could, say, compare some sizes here. So it might not be perfect because we are now sort of going from one row to another, but taking into account what we learned previous, let's try to rank these in order from smallest to largest. Okay, so smallest to largest. And this is by radius, so we're trying to rank them according to their radius. Okay. So we did learn that cations are smaller. Okay, so cations are smaller. So let's go ahead and say our cations, our 2 here, are probably going to be the smallest. So we're going to want to put them in. And we do know that the larger the magnitude of the cation, the smaller it's going to be. Okay, so I feel the smallest is going to be Ca2+, and then we're going to get K+. Okay, so that's our 2 cations, Ca2+ and K+. Okay, so now we know that generally, or that our anions are larger. Okay, so we'll put the neutral atom in here next, and then we know our anions are larger. So we have a -1, a -2, and a -3. Okay, so our -1 is going to be smallest, followed by the -2, and then the -3. Okay, so let's take a look and see how our prediction went here. Okay, so let's grab this. Oh, not upside down. Okay, there we go. So let's grab some of these values from this table right here. Okay, so I know it's kind of dark for writing, but we'll just go ahead and grab these. So Ca2+, according to this, is 1.14. These are probably in angstroms. Okay, so next we have K+, 1.52. Okay, so far so good. Argon isn't on here. I'll try to look that up possibly. Okay, or we can go probably to, oops, just went one too far. Argon here, 1.06. So I went back to my neutral sort of slide here. Okay, Cl-, 1.02. Okay, so we had a little bit of flip-flop here, but that's okay. 1.70. And phosphide I looked up, not on this chart, but I looked it up at a different source, 2.12. Okay, get our sort of lighting back here. All right, so the trend held up pretty good. smallest, next. Next, these two didn't quite work out, so these two pretty close in size here, but then got a lot larger here. So this was like our only spot here where it was tough to compare, where our comparison failed here. But for the most part, the trend follows. Our cations were a lot smaller, the anions were a lot larger. Okay, so it's held out pretty well. Okay. Oh, I'm so sorry. No, it did. I picked the wrong value. I picked neutral chloride at 1.02. Neutral chlorine, I'm sorry. Chloride is 1.67. Now this makes this so much better. So my apologies. So the correct value there, it does actually work out quite nice. Here, let me get the lighting back. It does work out. We didn't get a flip-flop. It would help if I looked at the correct color of dot. 1.14, 1.52. Did I look up the wrong one for K+? Nope, I did. That was fine. 1.06. So this one, again, still a little out of place there. 1.67, 1.70, and 2.12. Okay, so this case, our neutral atom was a little bit smaller in this case. So our argon was a little bit of a fluke there. Okay, so next we're going to look at ionization. So ionization energy. So we're going to define this, and then we're going to start looking at trends and things like that. So ionization energy is the minimum amount of energy required to remove an electron from the ground state of an atom in the gas phase. Okay, so this is important. We do measure this in the gas phase because we don't want to include in there any energy that would say take something that's a solid and change it into a liquid, then change it into a gas, and then energy added would remove an electron. So if you start in the gas phase, then you can measure the energy you put in actually is taking an electron and removing it. So again, what this essentially means, you have your nucleus of your atom, and then you have your shells, and then you have an electron in here, so E minus, sorry. So energy in, and essentially what you're doing is removing this electron. So this electron is essentially going to N equals infinity. So when we calculate this, say using like the Rydberg formula, we just put in there essentially N equals infinity to solve for the amount of energy that you would need. So completely removing that electron from that atom. Okay, so how does writing these equations look? So for example, I1, so the first ionization energy, so this is to require to remove the very first electron. So we're going to look at sodium. So this would look like Na atom in the gas phase. Okay, so this would be going to Na plus an electron. Okay, so Na gas phase, which is so weird. We're so used to it being a metal and a solid, but again, by definition, in the gas phase. So this is the delta H for this is 496 kilojoules per mole. Okay, so that's the energy it takes to take a mole of sodium in the gas phase and remove an electron. Okay, so this is called I1, just removing one electron. Okay, so next we're going to look at I2. Okay, so I2, this is called the second ionization energy. Okay, so this one, we've already removed one. So we start off with Na plus gas. And so it's not the energy to remove 2 electrons. It's you remove the first one, and now you're going to remove one from the +1 charged cation. This would be going from Na plus to Na2 plus gas plus an electron. So the delta H for this process is 4,562 kilojoules per mole. Okay, so that's the energy it takes to remove 1 electron from Na+. That is a huge amount of difference, going from like 400 and something to 4,000 and something. So why do we think that is like such a huge difference for that? Okay, so let's look at sodium. So sodium is neon 3s1. Okay, where this is all nice and core and 1 valence electron. So for I1, we're removing a 3s electron. Okay, so this takes very little energy, low energy. Okay, because it's definitely valence. For I2, if we've already removed this one, for Na+, we would have our configuration is helium 2s2, 2p6. So for I2, we would be removing one of, the 2p electrons. So now we're removing a core electron. So this takes a lot of energy because that's removing a core electron. Okay, so that's why we see such a huge jump in energy going from one to the other. Okay, so we have a figure for this. So ionization energy here, this is our trend. Okay, so this is just looking at Earth's ionization energy. Okay, so if we take a look, hydrogen's pretty high, helium is really, really high. All of our noble gases are very high. Our nonmetals over here appear to be quite high. Our metals down here seem to be relatively low, which hopefully this makes intuitive sense to you. We do know that things over here with these lower ionization energies, they form cations. So it does make sense that if a cation is formed by loss of electrons, that it wouldn't take a whole lot of energy to do that. And these ones over here, where these are quite large, these are the ones that form anions. So it makes sense that it takes sort of too much energy to form a cation, so we're going to form anions instead. Okay, so that is our trend. Okay, so if we were to do our thing and draw out our periodic table, oh, sorry, this is a terrible sort of noble gas slide there. Okay, so our periodic table, sorry, let me fix our lighting. Okay, so if we look at how ionization energy increases this way. And ionization energy we saw increases this way. Oh, sorry, not that way, this way. Sorry about that. Here, we'll color that in for sure. Increase in ionization energy. Okay, so we saw the one with the largest ionization energy was helium right up here, so increasing energy this way and this way here. So the question probably you've gathered from looking at all of these periodic trends is why? Okay, so why do we, how can we explain the left-right trend? So how do we explain that the ionization energy is so much larger for our noble gases than we do over here? And the answer is pretty much always effective nuclear charge. So we do know effective nuclear charge is a lot higher over here, which means that the positive negative attraction is a lot larger, which means it requires way more energy to actually remove that electron. So effective nuclear charge, the positive charge is holding the electron tighter. So therefore requires more energy. Okay, so effective nuclear charge is a lot lower over here, so it doesn't take much to remove an electron. So how do we explain up-down? So the answer for this is N shells. Okay, so if you are a lot closer to the nucleus, so your distance from the nucleus is a lot shorter, you're feeling a more attraction to the nucleus. So remember that energy for positive, negative for ions and anything with charge is proportional to Q1, Q2 over D. So essentially why this one has such a larger ionization energy is because the distance between Q1 and Q2 is much smaller. So increased distance gives us an increase in energy. Okay, so that is our trend for ionization energy. Okay, so let's take a look at one more slide. So this one here has our first 7 ionization energies for a handful of, some of them don't go all the way up to 7, but kind of for sodium through argon, looking at a few ionization energies. Okay, so we saw the difference between sodium I1 and I2. So this zigzag line here represents taking a valence electron away as opposed to taking a core electron away. So the jump from one side, from the white side to the gray side, is huge and large for all of them. And that trend represents going from valence to core, valence to core, valence to core for all of these. But you also note, like, for example, aluminum, which we know forms aluminum 3+, it does require more and more energy as we start shedding electrons. So again, recall what does happen. As we start forming cations, the effective nuclear charge increases. So by removing the first electron for aluminum, we've increased the effective nuclear charge. So it's holding on to the second one just a little bit tighter. So to remove that one takes more energy, and then more energy for the third one, because again, we have increased the effective nuclear charge by taking away electrons in the same shell that shield each other. Okay, so that's what we have here. And so again, you can see this as you work your way through the huge jump going from valence to core. But again, as you start taking electrons away, it does take more and more energy to remove more electrons, because again, you are increasing that effective nuclear charge each time you take an electron away. Okay, so a question, why is there such a large jump from I3 to I4 for aluminum? So going from I3 for aluminum to I4, again, that's because we have a valence electron, and then you're ionizing a core electron, which does take an awful lot of energy to do. Okay. So that's probably a good place to stop here. We'll have one more lecture on looking at electron configurations of ions in a little bit more detail, and then finishing up with our last trend called electron affinity.